Good day, everybody. Welcome to Algebra 2. Today we are going to finish our lecture over section 1.1 involving relations and functions and some terminology involving something that's continuous or discontinuous or discrete. Also, the main things of domain, codomain, range, one-to-one, and onto. Lots of definitions, so you definitely want to consult your notes from yesterday and take a look at those. I'm sure we don't have those all memorized quite yet. The warm-up today, if you're at home, you don't have to write it down, but I do encourage you to follow along and try to figure out what we're doing. For each graph, state the domain, the codomain, the range, whether it's one-to-one or not, whether it's onto or not, whether it's continuous, discontinuous, or discrete. Okay. Let's write down number one. Let's just make a list. They're all going to be the same thing every single time. We're looking for domains, codomains, ranges, whether something is onto. That's a yes or no question. Whether it's one-to-one, that's a yes or no question. And whether it's continuous or discontinuous or discrete kind of stuff. So we're just going to look at each graph one by one and go through it. All right, terms from yesterday. Domain are all the x's you're allowed to plug into your function. So you look at the number one right here, and you go along the x-axis. Is there any spot on the x-axis where the graph doesn't exist? And you got to use your imagination. What do these lines mean? They mean that it goes down forever. Yeah, all the way down to infinity. Does it go all the way to the left? Eventually, it's just slowly creeping down. Does it go all the way to the right? Yes. So it goes all the way from the left to the right. How far is that? From negative infinity over here all the way to positive infinity. And the way we're going to write that is negative infinity to infinity. New terminology, new things to think about. Glorified way of saying it exists everywhere from the left to the right. That's what domain's about, the x's. Codomain and range are about the y's. Where the codomain is where can it exist, not where does it exist, but where can it exist, up and down. And the range is about where it actually does exist. Now, pretend the graph's not there. Where could this graph go? Could the graph have gone all the way down to here? Before I drew it. It could have, right? I didn't draw anything, right? Could have been up here. Yeah, it could have been anywhere, correct? It could have been all the way down to negative infinity up to positive infinity. That's your codomain. Negative infinity to infinity. The things you could get out. Could. Before you even graphed the thing, before you even looked at it, pretend that graph's not there. Where could it have been? It could have been anywhere from down here all the way up to there. The range is actually about where it does exist. So now you actually look at the graph. Does the graph go all the way down? The arrows imply it does, correct? So it does go down to negative infinity, all the way up to, where's the highest level you think number one goes up to? 1, 2, 3, would you all agree with that? So it's going to be from negative infinity up to 3 this time. Negative infinity to 3. Does it actually get up to 3 or does it get close to 3? What do you guys think on the graph? It's a opinion. What do you think? Do you think it gets up to 3? It actually gets up to the number 3 or just gets really close to it? What do you think? No wrong answer. Anybody? Do you think it touches it? I would agree. I think it actually does get up to 3. Now, if something does get up to a number, it actually hits it. You don't use a parenthesis. You use a bracket. That's something that we all just get used to as time goes on. We'll be doing parentheses and brackets all year long. Notice the infinities have parentheses around them because parentheses mean you don't get there. Can you ever get to infinity? No. No matter how high you climb, you never get there, right? So something that you get closer and closer to but never actually get to, you use parentheses. If it actually does get there, you use brackets right there. Okay. What else we got to do? Is it onto? What's the definition of onto? Does anybody take notes yesterday? Anybody got it? Oh, good kids. Look at you pulling things out. You know stuff. Why are you late? I don't want to find my more. Okay. All right. All right. What in the world does onto mean? I'm skipping the one-to-one. We'll come back to that in a minute. Is it onto? Perfect. When the range equals the codomain. Well, here's the codomain. Here's the range. They're not the same, are they? So it is not onto. No. No for onto. One-to-one, there was a test that we went over yesterday that you can use to check if something's one-to-one. It's not a vertical line test. It's a horizontal line test. And if you look at this one, does it cross the graph only one spot? No, so it is not 1-to-1. That's your test right there. If it only hits the graph in one spot every time, no matter what line you draw, it is 1-to-1. Is it continuous, discontinuous, or discrete? That's a different concept. Continuous just means you can draw it without picking up your pencil, basically. Could you draw this picture of the graph without picking up your pencil? I think you could, right? I could just draw this, and I would never have to pick it up. So this is, in fact, continuous. Continuous. And there's your answer for that. If you're at home, that's what we got for our answers on number 1. After you get the gist of all these down, they're really not so bad. All right, let's go ahead and look at number 2 now. So same kind of deal. We'll start all over again. Domain, does it exist? Well, remember this line just goes on forever, correct? The arrows mean it goes on forever. Does it go all the way to the left? Yeah. Does it go all the way to the right? Yeah. So what's the domain again? Still -infinity to infinity. So write that down for the domain of this one. Number 2, the domain is still -infinity to infinity. Codomain. Again, if you erase the graph, how far up and down could it have gone? It still could have gone all the way down, right, to -infinity up to +infinity. So by default, 99.9% of the time, if they don't tell you anything, you can just automatically assume the codomain is -infinity to infinity. Range, though, where does it actually go? Well, how far down does it go? -infinity. How high does it go? So actually, this time the range is -infinity to +infinity this time. It does cover everything that's possible, which means since the range is the same as the codomain, it is in fact onto. It is onto. Yay. Is it 1-to-1? That's what I need my little test for. No matter what horizontal line I draw, does it only hit it in one spot? Yeah, so this is actually, yes, it is 1-to-1. And for the same reasons as in the first one, it is continuous also. You could draw that line without picking up your pencil, so it's a continuous function. Done. All right. Number 3. Here we go. Again, if you look at this thing left to right, you got to use your imagination, right? This thing just doesn't go shoot down. It shoots down, but does it slowly go to the left? Yes, it does. This shoots up high, but it slowly goes to the right. So again, the domain is -infinity to infinity. Again, it's possible this thing could have gone up and down forever. So again, the codomain is -infinity to infinity. That's pretty much always what you're going to write for this. Range, does it actually go all the way down and all the way up and cover everything in between? I'd say so, wouldn't you? Yeah, this goes all the way down. It does some wiggly stuff, but it goes all the way up. All the numbers were covered up and down, so the range is, again, -infinity to infinity. Since the codomain is the same as the range, it is onto. Is it 1-to-1? Let's do our little test. Oh, no, falls apart right there, doesn't it? Hits it lots of spots. That's not going to work, so it is not 1-to-1. But again, you could have drawn it without picking up your pencil. So it is, in fact, continuous again. Most things are going to be continuous or discontinuous. Okay. And the very last one, that looks pretty much like this one, doesn't it? What's the difference? There is a small difference. You see it? See a little part of the graph right there that's missing? Oh, that kind of jacks everything up. So what we're going to do is we're going to, let's be really careful with this one. Let's analyze it nice and slow. Ready? Domain. Does it exist everywhere from -infinity to infinity? What do you think? Everywhere from the left and the right? Everywhere? I see one spot where it doesn't. Do you? What x, and domain's about the x's, correct? So what x value does this graph not exist at? Wherever right here is, correct? What, 2? Would you agree as 2? Okay, so it exists all the way from -infinity until 2, correct? Not at 2, but then from 2 to infinity. Here's how you're going to write that. The first time you've had to do this. You're going from negative infinity until 2. Do you actually get to 2? No. Doesn't exist there, right? What do you use when you don't actually get to the number? Do you use parentheses or brackets, guys? Parentheses, good. So this is how I'm going to write that first chunk. From negative infinity to 2, we're cool. I got to skip over that little hole thing, that little hole in the graph. I don't know what the heck that thing is, but it doesn't exist. And then from 2 to infinity, we're good. So there's like 2 pieces here. There's another piece that starts from 2 and goes to infinity. A parenthesis on that one, again, for the same reason, because it actually doesn't touch 2. And this is new. When you have 2 pieces like this, one piece and another piece, here's what I want you to put in between. I want you to put a big U. Stands for union. Don't worry about what it means right now. But it's a union like anything else. It brings 2 things together. So it's like this piece or this piece. They're kind of put together right there. And you're going to write those kind of things a lot. So what's the moral of the story here? Is your domain always negative infinity to infinity? Not always. Most of the time it is, but not always. You've got to look at the graph and kind of understand it from there. Codomain. Had the graph not been there, what could it have been? It could have gone all the way from negative infinity to infinity, correct? Codomain's always an easy one. Negative infinity to infinity is cool. I'm down with that. Range, though, does this thing cover all the numbers up and down? I don't know. Certainly goes all the way down to negative infinity, right? It's here, it's here, it's here, it's here. Does it equal 1? Where y is 1, does it equal 1 there? Or does that whole jack it all up? You tell me, up and down. Does y ever equal 1? Here's where y is 1, right? Does the graph exist at that spot? No. So it covers everything from negative infinity up to 1. We got to skip over the 1, and then it's everything from 1 up to infinity. So very similar to what we did with the domain, but we're doing it vertically this time. Negative infinity up to 1 is okay. Parenthesis on the 1 because you're not actually touching it. Then there's another piece from 1 up to infinity that's cool. And there you go. Does that make sense so far? Are we okay? Help me out. I need to know what you guys know and what you don't know. So cool. All right. Is this onto? Is the range and the codomain the same? No, they are not. Therefore, this is not onto. Is it 1 to 1? Well, what do you got to do for that? You got to get your graph back out, and you got to do your little horizontal line test for that. No matter what horizontal line I draw, does it only hit the graph in one spot? You tell me. Yes, it does. So this is, yes, 1 to 1. Now be careful on this last one, continuous and discontinuous. Can you draw this without picking up your pencil? And I want to remind you that that little hole there means it just doesn't exist. So really what this graph is saying is it looks something like that, where there's just a little gap in the graph right there. Could I have drawn that without picking up my pencil? No. So that is not continuous. That's the other word, it's discontinuous. So we're going to write discontinuous for that one. And that's basically a review of all the skills we did yesterday in the lesson. So if you followed along with that and understood, most of it, then you're probably in good shape for day 1. Cool? All right, let's go ahead and do our learning goals now. Get those taken care of. You need to write these down when you're here. Whew. What should we do in math team this year, James? I know. There's not one competition in school. Maybe we could take a survey of what people want to learn, and we could actually have lessons over it. I don't know.
I'm kind of embarrassed, but I need you to reteach me the complete the square. I could
okay.
always plug it back into the formula.
Yeah.
You know me well enough. It's not enough for me. I want to know how it works. I want to
Why it works?
how to do it. Yeah.
Yeah,
I
sure.
don't want to just plug things in. I want to remember how to actually get it there.
Got it. No problem.
Then it just feels like cheating.
I understand. I don't think this lesson will take all hour, so we'll have some time at the end.
It's the only thing I have left on that.
Yeah. Really, we are just touching up things from yesterday. There's a few more things about sets that I want to talk to you about. What is a set? It's all this weird, funky stuff you've been writing, and you haven't, I mean, you kind of have a feel for it, but there's something more at a bottom level that we could talk about. Basic set notation today. That's about it. Then you'll have your online homework. Have you looked at it yet? How is that? I'm curious. You're the first people I've talked to. How is it reasonable? Make kind of sense? It's not too complicated, the online stuff? Really, I want to know, like, your honest feedback. It's good. I kind of like it too. I think it's kind of a cool curriculum, but I thought we'd run one or two of the problems from the homework together also, just to get your feet wet and stuff like that. But if you don't need me and you think it's easy, then I'll just shut up. I can be lazy and sit down. All right, I'll be lazy and sit down. I'll let you all struggle. All right, there's a couple things due today. So your syllabus should be turned in online, signed the last page. The multiple intelligence test should also be filled out and turned in online. If you haven't gotten that taken care of yet, that's okay. You still have till 3 o'clock today to get that done. The only homework other than that you have should be actually mathematically related, homework 1.1 on reveal, and that'll be due on Friday. Try to give you lots of time to get that taken care of. That's 2 whole more days from now. It's the first assignment, and I'm just giving you extra time to feel you out and see how that's going. And that seems like it's going okay, but I'll take surveys all day and see how the things are going. Okay, let's get back to notes. So take a second, and this is the notes for today. Got a whole bunch of things here. You might actually want to write down these middle 3 also. I know that's kind of a pain in the butt, but that would be easier. There's 3 main ways we can write a set of numbers. Sets are just collections of numbers. I like this curriculum better because we gotta learn sets and stuff. You guys never learned this?
No.
Mm-mm.
No, we haven't.
Never. It never came up. It never came up. No.
I don't even know what is the bar mean?
Such that.
Can't you also use like the backwards, the E thing? I don't have the name, but I don't remember what it is. It's like an epsilon and you do it backwards.
Yeah, that's exactly right, but not in set builder notation. You're right. If you were writing a proof and you're just writing language, yes, you're 100% correct. You remember. You're so smart, James. Basically, in this class, we're going to have to write a range of numbers a lot. The numbers from here to there are solutions. And there's lots of ways you could write them. The first is something you probably are very familiar with. It's called algebraic notation. You could just use an inequality. You could say all the x's less than 2. In the slide there, for example, and that picture shows you all the x's less than 2. So I don't know, if you're writing down the examples, you might want to write that picture too. But you see on that line there, the blue line is what is shaded in, and it's shaded in for all the numbers less than 2. So I could represent that by the inequality, x is less than 2. That's algebraic notation. That's old school stuff. There's nothing wrong with it. It's just we're going to use a little bit more mature notation going forward. So I do not want your answers like this. I don't want to see x is less than 2. I don't want to see x is greater than or equal to 5. I do not want algebraic notation. There's 2 other notations that I prefer. First one's called set builder notation. Now that one is one I want to expose you to, and I want you to understand, if nothing else, because a lot of your answers on reveal are in that notation. But for me, as your instructor, this last one, and we'll talk about both in a minute, interval notation, put a star by that one, because that's what I want pretty much all your answers for me to be in all year long. Interval notation, interval notation, interval notation. You need to know set builder notation too to get through reveal. And of course, I hope you know algebraic notation from just old school, middle school inequality stuff. But these last two we'll really concentrate on. Down the bottom in the box is a specific set that we'll use a lot in this class. You already see it coming up quite a bit, this notation of negative infinity to infinity stuff. Those are all the real numbers, all possible real numbers that exist. So they use a capital R for it sometimes. If you ever see a capital R with a couple bars in it, note that there's a couple bars in that thing. It's not just an R, but they have like two legs here and all this kind of stuff. If you ever see that, it just stands for all the real numbers, the real number line. And that just means everything from negative infinity to positive infinity. In set builder notation, which I'll explain more in a second, that would be that curly bracket thing with an X and a bar and negative infinity to X and great less than infinity and all that kind of nonsense. On tests, I want things in interval notation. On the board, I'll do things in interval notation. Reveal might have some set builder notation. So let's talk about that really quick. Okay. Set builder notation is really just good for saying, okay, I want you to give me all these things that meet a certain condition. That's all that this fancy stuff is going to mean. So if I said, on a practical example, give me all the students with red hair. That's just saying, give me all the students. I'm saying, give me something that have a certain condition about them. Or today, I'm going to give me all the students today that are in A through K in the alphabet or something like that. And I get a set and I get a group of people who are coming out. So they're going to write things like that a lot. Let's look at some practical examples. It makes more sense if you see things done with it. Let's say, give me the set of all X such that, this bar just means, separates things. This is the things I'm getting out based on these conditions, such that X is greater than 2 and even. You can even write words in this space. It's okay. So I'm saying, give me any X's that are greater than 2 and even. Can you give me a number that's greater than 2 and even?
4.
Thank you. 4. So this means the same thing as 4. Can you give me another one? Something that's greater than 2 and even?
6.
Thank you. I'm going to give you extra credit. 8, 10, 12, right? And it goes on and on forever, right? So you can have this set builder notation is a way to make any kind of set that you want that has a certain pattern to it, and you get something out from it. Sometimes they will put conditions on the front Look at that fancy nonsense right there. Anybody remember what this capital R thing means a minute ago? All real numbers. So they're saying, and this is a fancy symbol that just means, I guess you should learn it. Element of, it just means, give me all the x's that are real numbers. They're saying x's are this kind of thing. So give me all the x's that are real numbers, which are any kind of number, correct? But the x's have to be less than 1. So there's any number less than 1, 1, 0, -1, -2, all the way to how far to the left can I go? Negative infinity, right? So basically, this is all numbers from negative infinity up to 1. This is the same thing, and you could write this as negative infinity to 1. When we write this, which is in what notation? Interval notation? It's just saying the same thing as this right here. All the real numbers that are less than 1. This is a faster way to write that than all this nonsense. Would you agree? That's why I'm going to write things like this all year long. But at the bottom level, remember what this thing means. This thing means I'm asking for all real numbers that are less than 1. That's what this thing means. It's a shorter way to write it. Let's try another one. Okay, might want to write that one down. That's a weird little funky thing right there. This n thing, I have not introduced that yet. This might come up in reveal or something like that. They might use all kinds of different letters. Capital N is the set of natural numbers. Natural numbers are the most natural numbers you can think of. I'm talking like from baby level on. When you're a baby, what's the first things you learn about numbers? 1, 2, 3, 4. Natural numbers literally are just 1, 2, 3, as high as you want to go. So when I say this right here, I'm saying, what kind of numbers can I get out? I don't want just any kind of number. I don't want decimals and fractions and weird things. Only what kind of numbers? X's have to be natural numbers. So give me all the numbers, 1, 2, 3, 4, etc., that are meeting this condition where x is greater than 9. So what kind of natural numbers could you give me that are greater than 9? 10, 11, 12. So this is just a fancy way of saying 10, 11, 12, etc., etc., etc. Don't let this stuff scare you. You might want to write down some of the common sets since they're coming up all the time. Write these down. The natural numbers. We just went over what those were. Those are just the numbers 1, 2, 3, 4, forever and ever and ever. There is something called the whole numbers. I don't think this comes up, but we'll write it anyway. It's the same exact thing with one special number added. 0. So 0, 1, 2, 3, 4. Whole numbers. You might want to write down what these are too. These are natural numbers. These are whole numbers. These are things you did learn about along the way in Algebra 1 and stuff. But now I'm saying, hey, we have specific names for them, for collections of things. Got this weird looking Z thing. That's all the integers. All the positive and negative versions of the whole numbers. It goes forever in both ways. Those are the integers. The reason it's a Z, because in German guys who name that integer is called Zahl. So Zahl is integers and stuff like that. This one might come up too. A Q. This is the set of all fractions. but a more mature way of telling you what fractions are rational numbers. And lastly, the one we just talked about, big old capital R, that comes up all now. That's all the real numbers, which we'll usually write as negative infinity to infinity. Now, I do not expect you guys to memorize these. I mean, you should. The older you get, the more you should know what these things stand for and stuff. But just in case reveal brings up any of these symbols and says X is one of these things or Y is one of these things, it doesn't have to be X's, by the way. I've been playing with X's all day. It could be Y's. It doesn't matter what the letter is. In case these happen to come up in your work, now you know what they stand for and can apply them. Cool on that? All right, I don't want to belabor it. Let's go ahead and take a look at an example real quick, and we will see if we can call it a day. Here we go. Example 6, set builder and interval notation. Here's this graph right here, and the graph will extend to include all X values. The domain is all real numbers, so we're looking for all the X's such that X is, this just means is, what kind of number? What kind of number is it supposed to be? A real number. So right here in this top one, what I would write is, if they ask me to fill in the blank, I'm looking for all the X's such that something is a crappy epsilon. Something else. I would say all the X's that are real numbers. That's kind of all I'm just filling in the blank. I'm looking for all the X's such that X's are the reals. It makes sense. That's what they're saying, right? What else is saying? Oh, they want me to write another way. This way is called set builder notation. We're not going to do it much, but what would Mr. Cheney want to see on the test? How do I write all the real numbers from negative infinity to infinity? So your answer would be negative infinity to infinity on that one. So that would be your answers for your domain. People at home, this is what the answers would look like. You're looking for all the X's such that X is a real number. That's what they said. And interval notation would look like that. Lastly, we got the range. Range is about up and down. That's not about X's, is it? That's about Y's, correct? But there's no reason I can't do the exact same concept with just the letter Y instead of X. So let's see here. The least Y value for this function is, what's the least Y value? What's the least one it goes down to? What's the smallest Y value you see it hit? I would agree. I think the answer for that first blank would be -6. Check. The range is all real numbers greater than or equal to -6. So -6 up. We agree with that? Okay. How in the world am I going to write that in set builder notation? Kind of just leave it blank, right? They say the set of all Y such that blank. Go back to old school stuff. How do you say something's greater than or equal to -6? Just like middle school. Wouldn't you just say something is greater than or equal to -6? The things we're talking about are Y's, right? So I'd say, give me all the Y's such that Y is greater than or equal to -6. That kind of is cheap, but it works, right? It's easy. And then what's another way we could write that? Well, in interval notation, -6 to infinity, correct? Now, does it hit -6? Yeah, so should I use a bracket or a parenthesis, guys? Bracket on that one, very good. So, bracket, -6 to infinity. You always want to go bottom to top, left to right, bottom to top. Bottom's -6 all the way up to positive infinity. And that's kind of how I'd write my range on that one. That'd be my kind of my solution right there. And that's about it for set builder notation. Just learn this to get through reveal, okay? I'm not going to give you a thing on your test that says write something in set builder notation, okay? I want you to be exposed to it. I want you to, if you see it on reveal, to not freak out, okay? But on your test, what do I want? Crap like this over and over and over for me. Cool? Okay. You only got a few minutes left. It sounds like you don't need much help with the homework, so I'll just let you work on that for the last 8 minutes or so. Maybe get a couple problems done. Everybody's okay with doing the homework, really? Okay. All right, I won't worry about you then. So get that taken care of. Tomorrow will be a work day, which means since you're gone, basically you have nothing to do except for get this homework taken care of. So a cleanup day Friday, we will move on and have more material. but take the rest of the class today and tomorrow to tidy up that online assignment and get that taken care of. Good job, everybody. Love ya. And I'll talk to you all later. Bye.